Now we see some attacks on public key cryptography. So there are several attacks. Some of them are very sophisticated, and we'll see them better in lecture 9. For the moment, we will have a look at some attacks on factorization. So factorization, you can factorize fast, factorization of integers. If you can factorize fast, it will give you the break of RSA. So we have n, which is p times q prime. From n, we must get p or q. There are two main strategies to do that. The first strategy is to find x and y such that they are congruent modulo p, one of the two primes. This strategy leads to several attacks, and the most famous is Pollard's row attacks. And we'll see this in lecture 9. The other strategy is due to Fermat, so it's a very old strategy. And we need to find x and y such that x squared is congruent to y squared modulo n, where n is the composite number. Now, what we need here is that x is not congruent to y, and then x modulo n, and that x is not congruent to minus y modulo n. In this situation, we have decomposition, should be congruent to 0 modulo n from this equation. So n will divide x minus y, x plus y, and p or q will be effectors. These factors will be somewhere in these two factors. So what we do, we compute the GCD, between x minus y and n, and GCD between x plus y and n, and it's likely that one of these two will be either p or q. However, one thing is looking for x and y with this property. One thing is to find them which are not trivial, so this is difficult. Also in this case, it's not easy to find two numbers with this property, but not satisfying these. So Fermat's general idea has to be refined. So we have the general idea from Fermat. X and y. From this general idea, we have 5 different versions in nowadays algorithm. So the easier version, the easier modern version of Fermat's attack is called Dixon's algorithm. And we'll see in a couple of minutes. Then there is an idea based on continued fraction. Then we have a method called quadratic sieve. Then we have chunks attack. And finally, the most sophisticated but also the most efficient is the general number field sieve. So you will find usually abbreviations for this. So this is usually, you will find somewhere GNFS, and for the continuum fraction you'll have GCF. Okay, so we describe this, and we'll say something about that. So now we talk about Dixon's algorithm. Okay, so Dixon attack. So, first of all, we have to explain what are smooth numbers. We choose a base. These are primes. So you take some primes, P1, Pm, and you call this a factor base. Then you take an integer, k, and you say that k is smooth on B, k smooth on B if this integer is smooth on B if it can be factorized using only the primes in the basis B. If and only if k has a factorization in B. Then there is a special case if k can be factorized as a product of consecutive, as a product of primes, such that all primes are less than a number y, then we say that k is y smooth. We give some examples. So, for example, we consider a basis given with 2, 3, 5, and 7. So this is a factor basis. Now, we consider 392. The factorization 392 is 2 cubed, 7 squared, and then we consider 128. The factorization is 2 to 7. Now what happens? These two numbers can be factorized using only the primes in B. So these two numbers, 128 and 392, are B smooth. Also note that 128 needs only 2. So 128 is 2 smooth. And we could also say that 392 is 7 smooth, because we don't need more than 7. So we need this definition, factor basis and smooth numbers. Okay. So, we are ready to talk about the algorithm. First of all, we choose a factor basis. So choose B, a factor basis, P1, Pm. So remember, we have to factorize, and which is p times q. Now, how we choose this basis, we'll discuss later, but we choose it somehow. For example, it can be all the force primes. Now, we need a function, then we choose f, a function, from z to z, with the property that fx is congruent to x squared modulo n. And also we consider, we choose random some numbers, we don't know how many we need, we construct them randomly, r1, ri, and on these numbers what happens is that the f of ri is congruent to ri square modulo n, but is different from ri square. Okay, once we have these numbers, we have to search an index set U with a very special property. We want that the product for the U of the f ri can be decomposed in B. It's B in B with square product. So we want this to be B smooth. So we need this product to be B smooth, but more, we want this product to be written as even powers, a sum P1 A1 PMMM square. So we hope to find a set of these ri's with this property. The product of f of the ri can be written as a factorization of square powers of the primes in B. So this can be very difficult to find such a U, but we'll discuss that later. Now suppose we have the B, suppose we have a ri, we have f, and U. How do we attack? Okay, so we have this product for U of Fi, which is actually a product of, say, J in B, P1, A1, Pm, no, sorry, which is M square. Okay, we have this. Now we consider this number and we call this number y. On the other hand, we consider the product of all ri and we call this x. So now we have two numbers, x and y. What's the relation between these two numbers? Well, by definition of f, the product of Fi is congruent, so Fi is congruent to Ri square. So the product of Fi, of all the Fi's, will be congruent to the product of Ri square. So it is congruent to the product of Ri square, modulo n. So this is the key relation. Now, this product is actually y square. So y square, and this product is actually x square. So we have y square is congruent to x square modulo n. And now we proceed. We found Fermat's relation, and now we just compute the greatest common divisors. If from this we get P of Q, okay. If not, if we get N or 1, then we take other arrays and we iterate. So by definition of, by property of F, we have this relation, very important, this congruence. Then, by the factorization of these products, which is a property of U, we have this factorization that allows us to write Y square here, and the arrays are X square. Now, to understand this better, we give first an easy example. So we have factorized some numbers, n q, and we have chosen a factor basis of 3 primes. Now suppose that we have chosen R1, we compute f R1, and what we get? We get a factorization of kind P1 cube P2. Okay? Then we take R2, and we see that it can be factorized in this basis. So we dump it. Then we take another R2, and this time FR2 is, for example, P1, P2 square, P3. And then, after trying some random numbers, we find an R3 that we can factorize F over 3, and it is P2, P3. Now, what happens? Now we have the key relations. Now we just take U, all indices, 1, 2, and 3. From one hand, we have the product of the FRI, phi U. It's the product of all these. So we have these numbers is P1 cube times P1, which is P1 4. P2 is P2, wait a second, no, P2 is P2 here, so P2 4, and then P3 square. So we have this decomposition with even powers. So you just take Y, is P1 square, P2 square, P3. And X is the product in U of the array. So X is the product of R1, R2, R3. And then we have the relations. X square congruent to Y square modulo N. And we did the greatest common divisor, and we go on. However, in this case, U is very easy. We're just following what we found, one after the other, until it works. So, for example, if here we didn't have P2, we would have an odd powers for P3, and the attack won't work. So we have to find something else, and so on. Now I'll give you a detailed example in a more complex situation, so you will understand how we can use linear algebra to solve efficiently this problem. Before going into that, I'll show you here what we could do with that approach. So we have P1, P2, and P3, and we have the decomposition. So f of R1 is P1 cube P2. Now, what do? We write the vectors with three components corresponding to the three primes in the vector basis. Now, P1, we have a node value, so we can put 1. So we are taking the power, and we are looking at the power modulo 2. So if you went Pi AI, we put AI reduced modulo 2. So this will be 0 or 1. So 3 is 1, P2 is 1, P3 is 0, 0. Now if we do the same with the others, we'll have FR2, which is P1, P2 square, P3. So P1, 1, P2, 2, 2 is 0, modulo 2, 1. And then if we do FR3, we have P1 to 0, P2 and P3, 0, 1, 1. Now, what can we see? Observe that the sum of these vectors is 0, 0, 0. 1 plus 1 is 0, 1 plus 1 is 0, 1 plus 1 is 0. What it means? It means that if you do the product, when you do the products, the powers sum. And so, if you do the product of these three numbers, you will have a node powers of P1 times a node powers times an even power. So, odd plus odd is even. Even plus even is even. And the same for the other two components. So actually, it's very easy for us. When we have a factorization, we write these vectors. And so for any R1, we get vectors, which are only binary vectors. And what we do? The first time that we see linear relation, the linear relation in F2 is a sum to 0, we found the product, where all powers are even, and we finished. And now I'll show you a detailed example. We are now ready for a more detailed example. So first of all, we have our problem n. n is 4097, which is 17 times 241. Now we choose a vector basis with the first primes 2, 3, 5, 7, 11, 13. So we've chosen this, and we see if it works. Now as f, the function f, we take simply fx is x squared, and then we reduce modulo n. Now, the Ri that you have to choose random, we take them greater than the square root of n. Why? Because we will have that Fri is congruent to r square root of n, obviously, from the definition f. And we will have that Fri will be different from Ri square. Okay, so we start the algorithm. So we first take an R1 random. So the first R1 that we take is 65. F is 128, and it happens to be 27. So this R1 is B smooth. We can write the vector. So the components correspond to 2, 2, 3, 5, 7, 11, 13. So 2 to the 7 is a node power for 2, 1, and an even power for anything else. So 0, 0, 0, 0. Now we take another 2. Let's say it's not B smooth. Then we dump it. Then we take an R2, which is B smooth. Let's say 73. F to 73 gives 1232, which factorized is 2 to the 4 times 7 times 11. So an even power for 2, an even power for 3, for 5, an odd power for 7, an odd power for 11. Then we take R3, which is smooth, 92, 270, 2 to 3 cube, 5. So 1, 1, 1, 0, 0. Now what happens? We have arrived here. We are looking for something that sums to 0 in the binary world. Now if we try to sum, we don't get 0. There's no way, because 1 plus 1 is 0, but then 0 and 1 is not 0. As you can see, there is no way, if you sum all these 3, you don't get zeros. And if you take any 2, you don't get all zeros. So the algorithm says, go on, take another 4. Okay. Random, we get our 497, which becomes 1215, which decomposed is 3 to the 5, 5, which is 0, 1, 1, 0, 0, 0. And now we see what happens. So we are looking for vectors that sum to 0. And we have, look at this, if I want 1 and 1 to go away, I have 1 here, but then this one will be okay. Then we have this one and this one. So we have a false choice. So the first, the third, and the fourth. So we found our U. So given B and F, somehow, we are telling you how to choose U. U. So U is 1, 3, and 4. So the product of the array U is 65 times 92 times 97, and this number will be our x. Then we consider the product of Fi, and this is 2 to the 7 times here 2, 3 cube 2, 3 cube 5 times 3, 5 times 5. All this, what is all this? Is 2 to the 8, 3 to 8, and 5 squared. So it's this number square. This number is y, and so now we know that a square is congruent to y squared modulo n. Unfortunately, if you do the computation, in this case, you have that x is congruent to y modulo n. No. And so we can't use these numbers. However, we don't despair. We just go on with the algorithm. So this choice is unlucky for u. We look for another u. So we take another random, R5, 93, F is 455, decomposition 5, 7, 13, and so it is vector. 149 is 1716, decomposition is 2, 4, 3, 11, 13, this is the vector. And now we see that we have another relation. In fact, we have this one here, these two ones, they could go away. So, we have a candidate here. But now we have a 1. So, we need this one. And so, these ones on these columns are okay. Now we have 1 here that goes away with him. Then we have 1 here. And this one isn't going away with anybody. We need to call one of these. So we call this, and now it's done. In fact, in fact, 1 plus 1 is 0, 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 0 plus 0 is 0. So now we found a linear relation. So now we know u. How we get u? So we said R2, R4, R5, and R6. So x is R2 times R4 times R5 times R6. So u is 2, 4, 5, 6, and x is 73 times 97 times 93 times 149. What about y squared, the product of the F5? Okay, then we take R2 is 2, 4, 7, 11. Then we take R4, 3, 5, 5, R5, 5, 7, 13, R6, 2 square, 3, 11, 13. So this is y squared. So y is the square root. So y squared is 2, 4, 6. So the powers of 2 are 4 plus 2 is 6. So y is 2 cubed. Then powers of 5, 1, 2, so 5. Power of 7, 1, 2, 7. Power of 11, 1, 2, 11. Power of 13, 1, 2, so 13. And then the power of 3, okay, put them here, 5 and 1, 6, so cube. So the conclusion is that this x square is congruent to y square modulo our n. And what happens? If you compute the greatest common divisor of x plus y at 4097, you'll get exactly one of the two factors. So try this and check.